Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, welcome everyone. It's my pleasure to introduce Ola Svensson from EPFL. Ola works in approximation algorithms, and over the years he keeps coming with some very nice algorithms, and today he's going to tell us about one more.
Okay, thank you. Good to be here. Yes, I will talk about the new approach for approximating ATSP, which is a classical problem, and then we'll see some application to some special cases of metrics. So, I think most of you know the problem, but let me start with a gentle introduction with some nice geography. So, so suppose you want to find the best ticket from Lausanne, where I'm working, to Lund, where I'm coming from. You can go to what do? You go to the web, fill in the appropriate details, then you push like the search button. Then you need to have some patience, because there's some algorithm working in the background. Then usually you find some good ticket. Okay, so maybe 200 euros would be the price.
What website is this? Can we use it?
Check my homepage. there is a bank account number. So this is an easy problem because it's the shortest path, right? Shortest path from Lausanne to Lund. But you could spice it up. So suppose you want to visit all these cities. So now we ask yourself, what's the cheapest way to visit all these cities? Or what's the shortest way? That's one possible solution. And this, of course, this is the TSP problem that we like a lot, and many books have been written about it. So I would say, this one of our classical benchmark problems in computer science, both from theory and the heuristics, it's been studied actually from the 1800s. Pretty nice. That's where you get the name Hamiltonian cycle from Hamilton. And, even though all this study, I think it's still a main open problem what we can achieve with efficient computation. And in many areas, both in heuristics, they solve bigger and bigger instances, but also from approximation algorithms. So in basically, there are two variants, and we don't have a good understanding of what we can do in these two variants. And the two variants that we have, that's the most simple variant, where you assume that you have symmetric distances. Okay, so you have, if you go from U to V, it's the same distance going from V to U. Okay, there you have the famous Christofides 1.5 approximation algorithm, which is like a 40-year-old algorithm and still the best. Maybe it's I don't know if the only algorithm he did, but it's a good algorithm to do. So it's a 1.5 and it's still the best. And then you have the asymmetric case. So it's more general because we don't make any assumption that the distance is symmetric. Okay, but you still have the triangle inequality. And this is the more general problem will be the focus of this presentation. So maybe some people find it, hard to motivate asymmetric TSP. Like it's more natural with symmetric distances, maybe. So let me spend one funny slide on why you should care about asymmetric TSP. So if you don't feel it's natural with asymmetric, you should come and visit Lausanne. So it's extremely hilly. So you can see, there's a big difference of going uphill to downhill. Okay, so now you know it's a nice problem. So let's look at the definition. So input, one way of defining this as follows. We have input and edge-weighted digraph. And so here is our input. And we have length. You should think of this as one-way streets. And on an edge, we have the length of the street. So it's 1, 3, 1. Now it's asymmetric, so it might be 5,000. And the goal is to find a tour that visits each city at least once. So note that I'm allowing myself to visit each city many times. Okay, that's necessary. Or it's equivalent to assuming a triangle inequality. Otherwise, the problem is extremely hard. You cannot do anything. Okay, so we want to find a cheap tour that visits each city at least once. So let me redefine this in an equivalent way using graph theoretical notions. Okay, so what do we want to find? We want to find a subset of the edges so that the graph is connected, because we want to visit each vertex. And it should be Eulerian, so it should correspond to a tour. So here Eulerian means that the in degree is equal to the out degree. And that's an equivalent formulation. Okay. So that's what we want. We want to find a minimum weight, connect an Eulerian multigraph. So I write multigraph because I'm allowed to use the same street many times. So you can have same copies of you can have many copies of the same edge. So that's the problem we're going to work with. Any questions? Okay, good. So we want to devise algorithms for this problem. So there is, we know one way, and that is to formulate a nice relaxation, often referred to as carp relaxation. And if you have this point of view, it becomes quite natural. So you have a variable for each edge, which you think of in the intended solution. This variable should equal the number of times you pass this edge, or you use the road. So then the objective function is just that you minimize the total sum, the weight of the edges, and the number of times you use the edge. And then you have to write down that you want the graph to be connected on a Larian. So Larian just means that you have a constraint for every vertex. This means the sum of all the edges going out from V should equal the sum of the edges going into V. So that's a Larian. And then you want to have that is connected, so you avoid any subtours. So for all the subsets of V, you have that there is actually just one outgoing edge. Okay? So this is also called Subtour elimination constraint because you want to avoid subtours. Okay? Yes. So that's the relaxation. So now the name of the game is to, we can find a solution here. How do we massage it into an integral solution without losing too much? Okay. So I would like to argue that, okay, so how do you do? So I think there are, in theory at least, there are two available approaches of rounding this LP. And they come by the intuition that we have two sets of constraints. So suppose I completely drop the red constraints. I forget about them. Then what is the LP? The LP says, find me an Eulerian graph that is cheap. Okay, that we can solve in polynomial time. Okay, of course, here you could put everything to 0, but think about everybody that has degree 1. Then it's a mean cost cycle cover. So then we get a polynomial time solvable problem. So if we drop one of the red set of constraints, then you want to find a mean cost Eulerian graph. In particular, you can find a cycle cover that is not more expensive than a Tor. So then it's easy to find an Eulerian graph if I don't have the connectivity requirements. On the other hand, if I drop the Eulerian conditions, then basically I want to have a connected graph. That's also easy, right? You can find a spanning tree. Okay?
I mean, actually, if you drop the red condition, isn't the solution x equals 0?
Yeah. So I said, okay. So keep that everybody has at least one edge incident to them. Otherwise, that's also an easy problem. So, but it's even easier if you drop the red constraints without adding any other. But yes, keep the constraint that every vertex has degree at least 1. Then it's also an easy problem. Otherwise, yes. Okay. So either you maintain Eulerianicity, but then you drop connectivity and you try to fix it, or you drop Eulerianicity, you get connectivity, and then you try to fix the parities later on. Okay. So let's see what kind of algorithms you get by looking at it that way. So if you drop connectivity, well, then you get this very nice, I think easy to understand, repeated cycle cover algorithm. Okay, so we have our graph. Now find a mean cost cycle cover. Okay, that has cost at most opt. It's not so hard to see because opt is one specific cycle cover. But the graph is not connected, so what you do is to find a representative in each component, find a cycle cover, cost at least at most, again at most opt, repeat. Okay, so here you have total cost at most 3 times opt. Okay, so you have basically the approximation guarantee you get is the number of iterations you repeat. Okay, so now if you're really unlucky, all your cycles will always have length 2, so you'll get like log base 2 and approximation algorithm. So now you think like, okay, I should not be really unlucky all the time, right? So you should get some cycles of length 4, in a significant fraction of the time. That turns out to be really hard to prove. So there was this very nice initial paper by Fiscal Albiette Maffioli in the 80s that proved this, analyzed this procedure. So it showed that it's a log base 2 and approximation. And then it took 20 years for Blaser to somehow ensure that you not always get cycles of length 2. Okay, so you get a 0.99 log base 2.
But that's with a different algorithm, right? Because you might.
Yeah, exactly. Yeah.
You might.
Okay.
It's not so unlikely that they would be.
Good. There are examples where the algorithm I present where you're not careful of selecting which cycles to pick gives you a log base 2.
And not crazy examples either. I mean, if the distances vary widely, then it's in your interest to find really, really small cycles that don't connect the far away.
Why? Why should I find small cycles?
Because they're cheaper. because you don't have to
but the
make a big
total
arc
cost,
to other places.
Yeah, but if all the edges have the same length, then the total cost is always n.
Yeah, sure. Well,
Yeah.
right, but if there are graphs. There are weighted graphs where this algorithm will do exactly what you asked.
Okay. Yeah, so, okay, good. He changes the algorithm slightly, but it's still amazing to me that it's... I mean, I'm not saying that it is really hard, but it's kind of amazing, I think, that it is hard to not do better than log base 2n. And the best here is by Mohit and Uri. They get a 0.67, I think. Right, 2/3 log base 2n approximation using these techniques. So by changing the cycles you pick. Okay, so that's the first point of view. Now we can also try. Okay, so we tried here. It seems to be hard to do significantly better than log base 2n. So what we can do is try the second point of view. So it's easy to find a connected graph. Okay, so that's the same thing as in Christofides, right? If you know in the symmetric case, you find a spanning tree, then you correct parities after finding the spanning tree. That's the 1.5 by Christofides. But now, let me just illustrate that this is also pretty hard for ATSP. Okay, so what I want to say is that in Christofides, you can find a mean cost spanning tree, right? And you can always correct it in a cheap way by paying at most opt over 2. For ATSP, the situation is very different, as we will see here. So let's look at this example. All the blue edges you should think of as being for free. The red edges are really expensive. So basically, if we want to find a cheap Tour, we only want to use one edge, one red edge. That's the best Tour. Okay, so let's try. So our algorithm is to find the undirected spanning tree. That would be a spanning tree like that. Okay. For example, that's a mean cost spanning tree because the blue edges are cheaper than the red. And now we have to verify the corrected parity of these two guys because this is out degree 1, in degree 0. This is in degree 1, out degree 0. And if you think about it, the cheapest way of doing it is you only need to use one red edge and the blue edge. So everything's great. You got the best Tour. Okay? But let's now start with another mean cost spanning tree. It's of the same cost. So both are mean cost spanning trees. Now let's look at the guys that we need to correct the parity of. It turns out to be these. Okay, and now if you think about it for a while, you can see that you actually need to use all the red edges to correct this, which is a bad thing. Okay? So if you make this example bigger, this can show that even if you cannot start with an arbitrary mean cost spanning tree in a symmetric case. So you need to have some further conditions. And this is a big in contrast to a symmetric case. Okay, so what to do? And then there was a very nice paper by Subtour, Germans, Orescaran, Madri, Saveri, who formalized what do you actually need to get, so we want our spanning tree to be cheap, right? But this example shows that we need another condition for this tree to be good for ATSP. And the condition, a sufficient condition is something called thin trees. It's not necessary, but it's sufficient. Okay? So it's a nice graph theoretic problem, which is actually unweighted. So suppose you're given a k-edge connected graph. A classical theorem says that if we're given a k-edge connected graph, then we can find at least k over 2 disjoint spanning trees in that graph. Okay? So this says that if I look at one cut in that graph, then there exists a spanning tree using at most 2 edges crossing this cut. Right? If I fix one cut, there exists a spanning tree only using 2 edges.
If it's exactly k, then you will have. So it can be more than k. It's
2 over k fraction.
2 over k fraction of that.
Right.
No. Okay, yeah. Okay, so let's fix a cut of size k. Then then clearly there exists a spanning tree of using 2 over k. Yeah. Otherwise, if we think an arbitrary cut, it's 2 over k fraction. Perfect. All right. So now, what does the thin tree problem says? Well, find me for a tree that is simultaneously good for all the cuts. So you don't fix the cut before selecting the tree. Now you select the tree, and it should always be good for all the cuts. Okay? And here alpha is the parameter. So clearly alpha has to be at least 2 by the argument we said before. But for what can we do alpha? Okay? So we want to find a tree that is simultaneously doesn't use much more than alpha over k. It shouldn't use more than alpha over k fraction of the edges. And this turns out to be a sufficient condition because then you can use something called Hofmann's circulation theorem. So without going to this, it's just if you have a procedure that finds an alpha thin tree, then it actually gives you an alpha approximation for ATSP. So that is a sufficient condition to approximate ATSP. Okay. But this condition also turns out to be a little bit hard to analyze. So in their very nice paper, the log n over log n, then they show that if I sample a random tree from the Alpha solution according to a good distribution, then I can select alpha to be log n over log n, okay, which is basically the upper Chernoff bound. So this gives you a log n over log n approximation. Then for special cases of planar and bounded genus graphs, they can show that there exist constant thin trees, which is good. And then there's a really nice result by Nima here and Cheyenne, who is also here other weeks, not this week, who show that actually there exists always a poly log n thin tree. Okay, so there always exists such a tree. So this implies that the integrality gap is at most poly log n. So unfortunately, so the proof at the moment is not constructive. It also relies on some generalization of the proof of the Cadison-Singer conjecture, which is not constructive. Okay. So at the moment, it looks like the red approach is much better than the blue approach. So now, I will present a new approach that is more similar to the blue approach. So maybe it's the comeback of the blue approach. We will see. So to summarize, basically the best approximation now is log n over log n. Best upper bound on integral gap is poly log n. But the best lower bound on integral gap is 2. Okay, so and even more encouraging, this is everybody that is I know that worked on this problem believes 2 is maybe probably the right answer. Like at least a constant. I believe in 2. But everybody at math believe in a constant. Okay. And I should say here, so there is no better guarantees for shortest path metrics on unweighted graphs. So suppose all edges in the initial case had the same length. Then we don't know any better guarantees than log n over log n or poly log n in integrality gap. And this is in contrast to symmetric TSP, because in this instance we know better than Christofides. Okay, so there was this sequence of papers. The last one by Sebo and Wiggen gives 1.4 for shortest path metrics. And it's not clear how to get anything better with these approaches for ATSP, because, in this, if I could convince you, the main difficulty in the cycle cover approach was to bound a number of iterations. And in the thin tree approach, we actually reduced to the unweighted graph problem. So it's not clear how to use that you have a shortest path metric. Basically, if you manage to use these approaches there, you would probably solve the general problem. Okay? All right, so what's our new approach? Okay, so remember that how we presented it, we have done LP with a blue set of constraints and a red set of constraints, and we got the 2 approaches by dropping one of them. Okay, so what we will now do is to keep the blue constraints, but also keep a subset of the red constraints. Okay, for a specific subset S. Okay, of all the cuts. And why do we do that? So we still want this problem to be easy to solve, but by introducing some cut constraints, we can hope that we can patch up the unconnected components by not paying too much. Okay? So if we have some control on which cuts to satisfy, this can lead to less cost when we patch things together. Okay, so that's the idea. So we somehow try. So in the cycle cover approach, it was trivial to find a cycle cover, but it was very expensive to patch it up. Now we make each iteration a little bit more difficult. Okay, not as easy as finding a cycle cover, but the hope is that this difficulty will help us patching it up cheaper. Okay. And the nice, like the easy statement to state using this is, if we have a shortest path matrix or node weighted graphs, then the integral gap is at most 15. And we can also get the polynomial time 27 approximation algorithm. So what this node weighted is a generalization of shortest path matrix. Okay. So here, what I mean is that every vertex has a node weight, 1, 5, 2, 1, And the length of an edge is just the node weight when it goes out. So the length of this edge is 2. The length of this edge is 5, 5, 5. Okay? Of course, it's not a complete graph, because then it's a very easy problem. So the length of any edge not present in the graph is the shortest path. Okay? So this generalizes the shortest path to an unweighted graph that was considered for symmetric TSP. All right. Yes, in this case, the value of the Tor is that. Yes, I had some example, for intuition for node weighted. Suppose you want to visit all these cities, then you have different weights based on where you want to go more often. So I like Chicago and Boston, but so I visit them in January, this January, and I'm from Sweden, but I've never seen something like that in my life. So it was so. Also, there is a more serious motivation, maybe. So it's not too far away from general metrics. Because the metrics that we actually need to solve for this problem has if you use the relaxation that we use, has a very special structure. So the edges that appear in our graph, first of all, you will have a laminar set family with a value for each laminar set. So suppose this set has value 1, this has 2, this 4, and this 3. And now the length of an edge will basically be the sum of the values of the sets it crosses. Okay? So in our case, basically what we have taken is a laminar family where we only have the singletons. If you would have a general laminar family, then it would be general metrics. Okay, so this is the situation for symmetric. For asymmetric, there is two kind of sets, if it crosses as going out or in. But basically, this is the situation. So general metrics have also a very nice structure if you use this relaxation. This follows by duality. Okay. All right. So what did we do? Yeah, so our approach. So remember, the idea was to find a smart C for which we can solve this problem. So let me now define what kind of subset of constraints we are considering and what the problems that we solve. And we call this problem local connectivity ATSP. So the input is an edge weighted, and the input is an ATSP instance, okay? The same as ATSP. But now you're also given a partition of the vertices. So here you have an ATSP instance and a partition of the vertices. And now remember that we always want to find an Eulerian set of edges, but also satisfying some cut constraints. So the cut constraints we want to satisfy is that each cut defined by partition should have at least one edge crossing it. That's the only thing. So here one potential solution would be this. This is an Eulerian subset of edges, and I cross each cut. Okay. So that's the kind of cut constraints we want to satisfy. We want to find an Eulerian set of edges that cross each cut. So if I have the singletons in my partition, then it's basically a cycle cover. But if I don't have the singletons, then it's different. Okay? That looks like easy problem, right? Or at least for me, it looks pretty easy. So the thing that makes it not too easy is that our objective function is also a little bit harder than the ATSP objective function. So in ATSP, you just sum up the weight of all the edges, right? So here, our objective function says that each component should be cheap. Okay? So let me define this in the unweighted sense first, so that it makes sense. Okay, so we say that an algorithm for this problem is alpha light if it always outputs a solution f, so that each component satisfies the number of edges over the number of vertices is most alpha. So this means that locally, it looks like a good Tor. Okay? So if we look at this component here, okay, I visit two vertices, and I use two edges. That's a perfect Tor. So alpha is 1. If I look at these vertices here, this component here, I use 6 edges, and I visit 5 vertices. So this is like a 6/5 approximate Tor. And what I'm saying is that it's an alpha light algorithm if each component locally is an alpha approximate Tor. Okay? So here's 1, 6/5. So, yeah. Actually, so what one can note here, any questions on that definition? So I want to find a subset F that crosses each cut, and each component should be a good Tor. Good here, alpha approximate Tor. So why is this easier than defining an alpha approximation for ATSP? So suppose, do you see that? suppose you have an alpha approximation for ATSP. What can you do? You run that, you get a whole Tor that has alpha, that is alpha approximate. Clearly, that is a component, that's the only component you have to worry about. So that's a solution. Okay. Okay. You can also generalize this definition to general weights, but people tend to get confused here. So let me just skip it, and remaining of the talk, let's worry about unweighted graphs. Okay.
Sorry, just the condition before this, the condition is that it has to connect all these pieces together.
The partitions. It has to cross. There has to be, each cut defined by these partitions one edge has to go out.
So each cut where you put some of the parts on one side and some on the other.
Yes.
So it's very similar to the log n approaches, except that there you pick a representative for the cut, and you only pick edges of incident.
Yeah.
Here you're allowing to pick any edges.
Yes.
And there also you say, okay, I will want to pick one edge out of this cut, but the only edge you pick are the edges incident of the vertex. Here you're allowing arbitrary edges.
Yes.
So, so it's the same as, sorry, I'm just being slow.
Yes.
It's the same as saying if you put a clique on each part of the partition, then the resulting graph is connected, right?
Yes.
It goes a bit.
Okay, that's a little bit misleading. So right now we found a Tor here, right? In this, I don't require you to find a Tor that the graph is connected after contract. That I don't require. I just require that each cut is covered.
Yeah.
So it's weaker.
No, so it's not correct what you said. You could have had, this picture is misleading. You could have had two disjoint things as well.
So if you remove that.
Yeah, I could have removed this here. This
Then
here
you
would not
still
need to
have
be
it.
there. Because then each...
No, because then there's a cut consisting of the left half and the right half.
Yeah, but
and you're not crossing that.
Yeah,
So
but...
you want the symmetric cuts of these.
He's
Meta
only
graph.
taking one of them on one side.
So take one side and there should be an edge going out.
So the cuts I worry about is this cut, this cut, this
I
cut,
see,
and
I
that.
see, I see.
And I could have
Each
removed...
one individually.
Yeah, I could have removed the... Yeah.
And you care only an edge coming out of the cut? Or both?
I mean, since it's O'Leary, it's essentially... Yeah.
I see.
No, but you do pay for the edges inside as well.
Yeah, I pay for all edges.
The constraint is just outgoing edge.
Yeah. But you might pick edges inside to keep it all linear.
Yeah, exactly. So as I did here, I picked some edges inside to maintain O'Learionicity. Okay, good. So yeah, it's easier, but actually our main technical result is that if you can solve this problem, then you can solve the ATSP problem. Okay. So if there is an alpha light algorithm for local connectivity ATSP, then the integrality gap for ATSP is at most 5 alpha. And 9 alpha approximate Tor can be found in polynomial time. Okay, if your algorithm for local connectivity ATSP runs in polynomial time. Okay, so this seems to give the power to patch things together. Okay. Now the problem. Okay, so we have an easy free light algorithm for node-weighted metrics. That's why we have for node-weighted. So you could generalize the definition for local connectivity ATSP to general metrics. But the only place where we can solve it, right, where we can define an alpha light for constant alpha is node-weighted metrics. So that's why we have a free light. So this gives you the 15 and 27 for node-weighted metrics. Okay. So so this free light, if you have, like this is easy to, at least for unweighted graphs, right? Like find a cycle cover, that's one light. Now you have to do some stuff when you have general partitions, but it's kind of not too amazing to think that there is not too hard algorithm for that case. So let me skip that and let me worry about how to prove this theorem, how to use this power to patch a Tor that is not too expensive. Okay, so what's the proof ID? Okay, so the first approach would be a little bit what Mohita hinted at. Well, we have something that very much looks like the log n. So we start with a completely unconnected graph. We solve local connectivity ATSP with the partitions, with the singletons as partitions. Then you get something like that, right? You get something that has, every vertex has outdegree at least 1. Okay, and these guys are cheap. This costs you at most alpha opt, because it was alpha light. Okay, so now we have connected that. So now we can run local connectivity ATSP on this partition. Okay, so you find this set of edges. Okay, so again you pay alpha opt. Okay, because that's not good. So here, here it was good because you only run 2 iterations. But again, if you do that, then the total cost will be the number of iterations times alpha times op. So it's even worse than we had before. So that's not great. So we have to do something special here. And I think what the most special thing is our initialization. And the initialization is also why we have these 2 different results for polynomial time and not polynomial time. Okay? So what is our initialization? So we do some lexicographic initialization. So here I have the graph. I didn't draw it. So now, of course we're going to use that we have an alpha light algorithm for local connectivity, ATSP. So what I will do in the initialization is think about, I will select the biggest cycle in the graph, and this will be my starting point. So my first thing I select is H1, I call it H1 star. That's the largest connected component that has a 2 alpha light Tor. Of course, if there is a 2 alpha light Tor in the whole graph, this is the whole graph, and we solve the problem. So this is not, that's why we have the non-polynomial argument and then a polynomial argument. Okay? So that's my first component. Why do I do that? So let's look at F. If that's a Eulerian subset of edges that is alpha light, then I claim that the number of vertices, the number of edges in F is at most alpha times the size of the number of vertices in H1 star. Why is that? So how am I? You know that the F is alpha light. So the number of vertices in F, number of vertices is at least F over alpha, right? Because it's alpha light. So if F is greater than alpha times VI1 star, that means that F is alpha light and also contains more vertices than H1 star. But that contradicts our starting point. We started with the biggest component that contained a 2 alpha light Tor. So then F should have been our H1 star instead. Okay? So that's what it buys us. Okay? So we know that everything that is alpha light that intersects H1 star has cost at most roughly V1 star. Okay?
Sorry. Did it use that intersects or anything? It just...
Yeah, it doesn't. Okay, good. Yes, it doesn't even need to intersect.
Yeah.
That's good. Okay, that comes in the next picture. So now H1 star was the biggest guy. Then I remove it. Take H2 star to be the biggest guy in the remaining graph. Now I say if F does not intersect H1, then it has cost at most alpha times V2 star. By the same argument. Because otherwise I could have replaced H2 star with F. And I would get a better lexicographic order. Okay. Okay, and I do this. Okay. The last guys might be singletons. Okay. That's my initialization.
I'm sorry.
Yeah.
Confused. Connected component of the graph?
Yeah. So
how can the Tour intersect it like that? I mean, if it's a connected component.
So think of this as a cheap Tour. Think of this as a cycle of the longest length in the graph.
But when you say connected component,
It's not it's connected, but not a component. It's a connected set which has this property, largest such. So the whole graph cannot be, then you have already solved the problem. So this is the largest subgraph which is connected and has this property.
So when you say
Is that what you mean?
I see. Yeah. It's not the connected component. Yeah, good. It's if I induce on the vertex in V1 star, then it has a Tor of size 2 alpha. So forget about connected
And are you
components.
claiming you can find such a thing?
No, that's what I'm saying. So I'm claiming that, of course, if I could find it, then I would just change 2 to 5 and I would be done. So that's why I have these 2 different factors, 3 and 9. Yes. Good. All right. So now we have done any more questions on initialization? Okay, so now we have our initialization. It costs us 2 alpha times opt, since each component is 2 alpha light. We have a Tor here using 2 alpha more than V1 star of the vertices. So what would our wish list of the merging step be? Well, one thing would be, okay, suppose we can connect the graph, but we only want to add alpha light components. Okay, so that we short H1 star at most ones. Okay, so this guy, he intersects V1 stars. We know that he has cost at most alpha V1 star, right? By the previous argument. This guy, he intersects, the biggest guy he intersects is H2 star. So we know that this guy, he has cost at most alpha V2 star. This guy, he intersects, the biggest guy he intersects is H3 star, so he costs at most alpha V3 star, and so on. Okay? This is at most alpha V4. So if we could do that, so here I charged H1, H2, H3, and this should be H5. This should be H5. So I charged everybody at most once. Okay, then I would be happy, right? Because then I would get 2 alpha opt plus another alpha for opt, because I charged everybody at most once. Okay, so that would be an ideal situation where we could charge everybody at most once. Okay, so that's unfortunately not completely true. So let me explain how we do it by looking at 2 extreme cases after the initialization. Okay, so first case, extreme case is that after initialization, all my starting components were of exactly the same size, let's say. It should be opt over k. Yes. It should be opt over, n over k, because we assume, it should be not opt, n over k. Okay, so everybody is of the same size. Okay. Why is it easy problem? Do you see why it's, okay. What is the size of any alpha light graph? Alpha light subset of edges in our graph is at most size V1 star, right? Which is opt over k. Okay. And now how many such guys do we have to add to connect the graph? Well, we have to add at most k minus 1. Like in spanning tree, we have to find like a connect the graph with k components. We have to add at most k minus 1 guys. And each guy has cost opt over k. Okay. So we have to add, so here we add, these are alpha light guys. And in total we added, here is 4 plus 6, so in total we added k minus 1 guys. But everybody, you know that that is what we proved before, that everybody has size at most V1 star, which is opt over k. We added k minus 1 many, so in this case you actually get alpha to patch things together, plus the initialization was 2 alpha. So this is a very good case, where the initialization actually resulted in even size components. All right, so let's look at the opposite case, where you have, after initialization, you got this huge guy, and now you have all these small guys. Okay. All right, so now we solve local connectivity ATSP, as we know we can do. Okay, so now everybody gets to the big guy, right? That looks problematic, because now I can only say that this guy is at most V1 star, this at most V1 star, so I will get a horrible approximation here. Okay. So here is the second claim. When we have such a thing, then the claim of the red edges is at most 2 alpha V1 star. Okay. And why is that? Okay, think about it. So the red edges, they are many more than V1 star. So at least the red guys, they contain 2 V1 star vertices, because they are alpha light. The red guys are alpha light, so they contain 2 V1 star edges. Vertices, they cover 2 V1 star vertices, which is more than H1 star. So let me do it here. Okay, so what we will do is to consider graph H star, which is the union on H1 star and all the red guys. You grad graphs. Okay. H star is the union of H1 star and all the red components. Okay. So now we want to calculate what's the number of vertices of this guy. Well, it's at least 2 V1 star vertices. It has R vertices. Let's say R is the number of vertices in these red components. That's at least 2 V1 star. Okay? Because it's alpha light, and we are supposed towards contradiction that it's bigger than 2 alpha V1 stars. It has at least 2 V1 star vertices. And now how many edges does this graph have? We know that H1 star was 2 alpha light. So H1 star has 2 alpha V1 star edges. The red guys are alpha light, So they have at most alpha times r edges. Okay, so it has at most 2 alpha v1 star plus alpha r edges. Now if you divide this by r, well, here you get at most alpha, because this guy is bigger than 2 v1 star. So here you get at most alpha. Here you divide by r, so you get alpha. So this means that in that case, h star was 2 alpha light. So if we suppose that the sum of this was bigger than 2 alpha v1 star, then h star itself was 2 alpha light, and clearly it's bigger than h1 star. So this would also be a contradiction to the initialization. Okay, so it's clear that one of them is at most v1 star, but what is nice is that actually the union of them is at most 2 v1 star, and that's what we use here. Okay, so now of course we are happy. So here it's 4 alpha. So okay, so this was 2 extreme cases, and the final 5 actually comes because you have to somehow combine these in a clever way. So you get 2 alpha from the initialization, you pay alpha for the first case and 2 alpha for the second case, and then you get 5. Okay, but I thought the merging was. So I stopped presenting the whole merging because people found it not so intuitive. But it gets a little bit, yeah. It's kind of short, but it's a little bit. You have to be careful in which order to add stuff to obtain this. Okay, some open problems. Let me finish with this. So we have presented a constant factor for node-weighted ATSP, and I said for shortest path metric for TSP, there is better than Christofides. But what about node-weighted TSP, symmetric TSP? So that is now defined as I have a weight for each vertex. The distance of an edge is the sum of its endpoints. Okay? That's a special kind of metric. And here, I've been thinking, I think several people have been thinking, and here we don't know how to do better than Christofides. So this is somehow in between the general metric and the shortest path metric for unweighted graphs. I think it's a good open problem, but yeah, I would be very interested in a solution. And then obviously there is this constant for ATSP on general metrics. So either you can find a fin tree, or you can solve this local connectivity ATSP in the general case. That's the 2 approaches we know. Of course, there can be other ones. Okay, so what did we do? I explained the existing approaches. Then we had a new approach that relaxes connectivity. And actually, you can improve it a little bit. So instead of having 15, you can get 13 for node weighted. But I have no idea how to, like 2 seems to be the right number, and I don't know how to get there. And there's a nice open questions in both cases. Okay, thank you.
Questions?
What happened? Okay.
Questions? So you didn't say, but like it's how to relate these to the LPs, but is that like that's kind of.
You can actually. So this the I don't know where it is. The main technical theorem. That's what you're referring to, right? So actually, that is very general. So the only thing you need to do. Sorry. Where is this? Here. So here we had a number of edges over the number of vertices, right? So the only thing you have to change is the weight of the edges, and then you have an assignment of weights to the vertices. So this LBV prime is just, I have an assignment of weight, the cost the LP pays for visiting this vertex. And the main theorem holds as long as this is a non-negative function and the total sum of weights you assign to the vertices is at most LP value. So you can assign it as you want. But the question is, now when you have assigned these weights, can you solve local connectivity ATSP? But you're free to assign them as you want. So for node weight, we just take, it's natural to take that the amount you pay for a vertex is simply the number of edges going out from it. Because all the edges there have the same weight.
I'll call again.